Hello APC Mechanics students, today we'll solve the past paper FRQ 2018 exercise number 3. As always, the figure appears to be above the text, so don't look below. A triangular rod shown above has a length capital L, mass capital M, and a non-uniform linear mass density, which means the center of mass of the object is not located geometrically at the center, given by the equation lambda is 2m divided by L square x, where x is the distance from one end of the rod. Perfect. Part A. Using integral calculus, so they provided for you the method, show that the rotational inertia of the rod about its left end is given by ml squared divided by 2. Then the integral is given by I, the rotational inertia integral of x squared dm. Now, before we handle this integral, we need to specify the boundaries. So remember that the thing, we should choose the origin to be at the pivot. Here they're specifying for us that we need to determine the rotational inertia about its left end, which means this is the pivot for us, which is the origin, and indeed we're integrating from 0 to L. So that's 0 to L. Now the next thing is to unify the variables, and this is done by considering the linear mass distribution. So we can say that lambda is given by dm by dx, and we're interested in determining what is the differential mass. Then in this case, the differential mass is given by lambda dx, and lambda is given by 2m divided by L square x multiplied by dx. Then the integral I from 0 to L of x square 2m divided by L square x dx. Now 2m over L square can be dragged out. Integral from 0 to L x cube dx, and the integral of x cube would be x to the power 4 divided by 4, and the boundaries are set for us to be 0 and L. Now you need to compute this twice, once at L and once at 0, and you need to consider the difference. You can ignore the 0. That would be 2m divided by L square multiplied by L to the power 4 divided by 4. And that would give you the factor half. L power 4 over L square would give you L square, and indeed we end up with the following rotational inertia. Now in what follows, they're telling us the thin hoop shown above in figure 1 has a capital mass M, radius L, and a rotational inertia around its center of ml square. Three rods identical to the rod from part A are now fastened to the thin hoop as shown in figure 2 above. So we have constructed the following system, which is the hoop rod system. Consists of 4 bodies. This is the hoop, and these are the 3 rods. Now in part B, they're telling us to derive an expression for the rotational inertia I total of the hoop rod system about the center of the hoop. Express your answer in terms of M and L and physical constants as appropriate. We know that the rotational inertia is an additive quantity. Then I total would be that for the hoop, which is given by ml square, plus 3, because we have 3 rods, 3 multiplied by half ml square, and here we're determining the rotational inertia around this point, which is the center, and indeed we have determined for the rod around this point. Then in this case, we have ml square, we need to add 1 plus 3 over 2, that would be 5 over 2. Then it's given by 5 over 2 ml square. And indeed our answer is being expressed in terms of m and L. Now in what follows, they're telling us the hoop rod system is initially at rest and held in place, but it's free to rotate around its center. A constant force F is exerted tangent to the hoop for a time delta t. In part C, we need to derive an expression for the final angular speed omega of the hoop rod system. Express your answer in terms of m, L, F, delta t, and physical constants as appropriate. So here what's happening is that the system is initially at rest. We apply a force F tangent. It will exert a torque for a certain time delta t. We need to find the final angular speed. We know that force produces acceleration, and they can be related to each other using Newton's second law. For rotation, then let me say apply Newton's second law. Now, it's not much important to mention whether it's for rotation or translation. The important thing, this is a big law that you mention. Now, torque net is equal to I multiplied by alpha. And what are the different forces that might act on the system? We have its pull of gravity, the force at the axle, let's suppose, and the tangent force applied to the hoop. Now, you can ignore the gravity and the axle because they pass through the axis of rotation, and the only force that produces torque is the capital F that we have. Then torque produced by F is equal to I alpha. Now remember that the definition of the torque is plus minus Ft cosine theta, in which theta is the angle between the tangential and the force. Here it's being applied tangentially, so we can ignore the cosine, and since they're asking for the speed, we can consider everything to be positive. So we're talking about magnitudes, then that would be F multiplied by the radius. Since it's applied to the hoop, then the distance from the force to the center would be L, and that would be equal to I. Since we need to express in terms of M and L, so let's replace I by 5/2 ml square. And now we can apply the cancellation effect for these. Then in this case, what do we have? We have alpha is given by 2F divided by 5 ml. But this is the expression for the angular acceleration we need to angular speed. And because the force is constant, then this is constant. And we know that from kinematics that omega is omega 0 plus alpha t. Initially from rest, as it has been stated here, which means that omega 0 is 0 and t would be represented by delta t. Then the final angular speed is given by 2f divided by 5 ml multiplied by delta t, and indeed our answer is expressed in terms of these. Now moving on to the next page, the hoop rod system is rolling without slipping along a level horizontal surface with the angular speed omega found in part C. At time t is equal to 0, the system begins rolling without slipping up a ramp as shown in the figure above. In part D, idea 1, on the figure of the hoop rod system below, draw and label the forces, not components, that act on the system. Each force must be represented by a distinct arrow starting at and pointing away from the point at which the force is exerted on the system. In other words, we need to do a rigid body diagram. Because the system has a mass, then it will be directly subjected to the pull of gravity. Always the first force that you should think of is the pull of gravity. And we need to represent it correctly at the correct point of application, and we know that it's being exerted on the center of mass. Although these rods are of non-uniform mass distribution, which means the center of mass will be located somewhere here, but due to the symmetry of the problem and because we have a hoop, the center of mass would be at the middle, so that's the pull of gravity down. There is a contact between the wheel and the ramp, then there will be the normal push perpendicular to the ramp. And notice that because they said at time t is equal to 0, the system begins rolling without slipping up the ramp, which means we have friction. And which friction specifically? We're talking about static friction, because it is the force that causes rolling without slipping. Now here the thing is that because it's moving up, okay, let me say before, we have static friction. We have two ways to represent static friction, either down or up. You can think that it is down because it's going up, and that's wrong, because the direction of friction is not basically related to the direction of motion. In a sense, it's not opposite to the direction of motion always. It is opposite to the tendency of slipping. So in this case, if you consider the point of contact here, and you think about the motion while the system is rolling upward, the tendency of slipping would be downward. So in this case, if you refer to the definition of friction, friction is opposite to the tendency of slipping, which means friction would be upward. So friction in this case would be represented up the ramp. You can consider it as a general rule whenever we have rolling without slipping. The direction of frictional forces, whether the body is rolling down or up, friction would be always up the ramp. Okay. And remember that friction should be represented from the point of contact between the rod, between the system and the ramp. Now in idea number 2, we need to justify your choice for the direction of each of the forces drawn in part DI. So we might expect such questions whenever we do an FBD or a rigid body diagram. Let's start by the pull of gravity and say it is down, and that's because the pull of gravity always points downward. Now for the normal push, in this case the direction of the normal push is given by up left, and we need to give the justification. The justification is given by the normal push points perpendicular to the surface, and finally we have friction. In this case friction is upright, and what's the reason? As we have mentioned, the point of contact have a tendency to slip downward, and friction points in an opposite direction. And finally, in part E, which is the last part of this exercise, they're telling us derive an expression for the change in height of the center of the hoop from the moment it reaches the bottom of the ramp until the moment it reaches its maximum height. So we need to find H, and here we're talking about conservation of energy, because initially at this point we have kinetic energy. Upon reaching the maximum height, all of the kinetic energy would be converted to gravitational potential energy. Pay attention, we need to express your answer in terms of m, l, I total, omega, and physical constants as appropriate. Now before we apply the conservation of energy, now here also we have static friction, but we can always apply the conservation of energy because friction doesn't perform any work and it doesn't dissipate any energy. So we know that from the rolling without sleeping. So, but first, before we apply the conservation of energy, we need to choose our PE level, and usually our PE level is chosen to be the lowest level surface passing through the center of mass in our problem. So let me say take the PE level to be the horizontal, passing through the center of mass. Of the hoop rod system at the bottom, then here, based on our choice at this point, when the center of mass is located here, the energy is purely kinetic. Now we can apply the conservation of energy. This is a big law, we need to mention it. Then apply conservation of energy. Now in this case, what do we have? We have energy initial is equal to energy final, and energy is about being kinetic and gravitational potential energy. So that would be kinetic energy final plus gravitational potential energy final. Initially we are at the PA level, and because we're interested in determining the maximum height of the center of the hoop, then the final kinetic energy would be 0. Now what type of initial kinetic energy do we have? So if you read the text carefully, the hoop rod system is rolling without slipping along a level horizontal surface. So basically it's rolling here, and it cannot roll up the ramp unless at this point it has some translational speed in addition to the angular speed that it has been gained previously. For this reason, I will write here half I omega square plus half. Now this is the tricky part. Now we need to add both energies given by rotational and translational. The translation is given by mv square, but what is the mass of our system, especially that our system consists of a composite body? Now the mass of the hoop is given by m, so this part has a mass m, and each rod has a mass m. So in total we have 4m, 3 for these and 1m for this. So in this case I'm gonna say that the mass is given by 4m, and our speed is given by v squared. That would be equal to the final gravitational potential energy given by 4m g, and we're interested in determining h. Now the thing is that we're interested in determining h in terms of ml I total omega, so don't try to split I, which is given by the total, because we need to express our answer in terms of I total. Unlike the previous exercise in which we have splitted I total, and this depends on the requirement of the part itself, we need to express in terms of ml, f and delta t independent of I total. Therefore, now the only thing left, we don't know what is v, but v can be related to omega. We can say that v is equal to omega multiplied by the radius, and here the radius is basically the length of each rod, which is capital L. So v is equal to omega L. Okay, and the reason is because we have rolling without slipping. So that would be half I total omega square plus half 4m omega square multiplied by L square is equal to 4mgh, and we're interested in determining h. Then h in this case would be given by half I total omega square. Now 4 divided by 2, that would be 2 m omega square L square divided by 4mg, and that would be expression to the maximum height reached by the center of mass of our system. And that's it for me in this video, guys. See you soon in a new one.